Swayam Prabha. Digital India. Educated India.
Okay. Now, having discussed fair bit of undamped free vibrations, let us look at damped free vibrations, which means that the term that we ignored earlier of the dissipating force or C x dot will now be included in the equation of motion. Of course, f of t will also be set to 0 for this case, and the new governing equation for the damped case is going to be this. Again, we assume the initial assume the solution to this governing equation as x naught e to the power s t. Do not confuse this x naught with the initial condition, x naught is any arbitrary constant. Now, if you substitute back into this equation, if you recollect, x dot was x naught s e to the power s t, and x double dot would obviously be s square x naught e to the power s t. So, when you substitute that, this is going to be m s square plus C s plus k s plus k, and all the terms will have this common term x naught e to the power s t. So, and for the same reason why we said that these two terms cannot be 0 all the time. So, the only non-trivial solution to this equation is to set this equal to 0. Earlier we had m s square plus k equal to 0, from there we got two roots of this governing equation. Right. Now, let us look at this again, it is a quadratic in the root s. So, obviously, there will be still two roots possible in this case. So, we all know that the roots are given by minus c over 2 m right. So, if you solve this quadratic, this is how the roots are going to look like. I can write this as can take this out in okay, and of course, you can as well simply write this you can either use that k by m as omega n, but I would prefer to keep it like that right now. So, you have two possible roots here, okay. One is S 1, the other one is S 2, and because there are two roots, I can get the general solution x of t to be some constant again e to the power S 1 t plus b e to the power S 2 t. Both roots will contribute in general, and that is the general solution of your vibratory system. Okay. Now, I can write this as a e to the power minus c over 2 m t I am basically splitting now this part and this part for even S1. Okay. So, if I take S1 to be this plus sign, then I have square root of C over 2 m minus k over m t, and then similarly I will have expression for B. It looks little involved, but will definitely give lot of good insights. Now, what you notice here, if you look at this entire solution, is that this part, what do you call this, exponentially decaying term? With t progressing or t increasing, you will have this particular term gradually diminishing. Same here. Look at this term, this as well as this. Now, if I focus on that particular root, okay, square root of C over 2 m square minus k over m. If this term is greater than this term, if this term is greater than this term, then what? It is a positive value. So, e to the power a t, that is how the term will look like, right. Whereas, if this is less than square root of less than k over m, then what happens? You have a square root of a negative quantity, right. How do you write that as j? Let us say if I call this as j p, right. So, instead of e to the power a t, if I have e to the power j p and then of course, t coming from here, what does this expression mean to us? Isn't it, right? So, instead of a solution which has e to the power a t, or in this particular case this is going to be minus a t. So, the reason why I have changed this e to the power a t to e to the power minus a t is that if you club the first exponential term, that is e to the power minus c by 2 m t, and e to the power square root of this entire term t, the second exponential term will have the coefficient of t smaller than c over t m of the first exponential term. So, effectively if you club the two exponential terms, then it becomes a e to the power minus a t, and that a is a constant, and which is basically combination of the two exponents of the two exponential terms. And so, the effective effectively it becomes e to the power minus some constant times t, and then it becomes an exponentially decaying term. There is a distinctly different characteristic of the response. This response is harmonic or oscillatory, I would call this, and this is non-oscillatory. Do you agree with that? So, whether the ensuing free vibration response will be oscillatory or non-oscillatory will be governed by the relative numeric values of these two terms, c over 2 m with respect to k over m, right. So, it all will depend upon whether this entire term will be positive or negative. If it is negative, the solution will turn oscillatory, there will be harmonic terms like cosine and sine, whereas if it is not, if it is positive, you will have a simple exponentially changing term, or it's non-oscillatory. And therefore, for us to figure out whether our system is going to be a periodic or a non-periodic one, we would like to introduce a term which is called as a critical damping term. Okay. So, this C is going to decide for a given system having certain stiffness, certain mass, it is the damping coefficient C which is going to decide whether the system turns out to be oscillatory or non-oscillatory. So, what we do is we take a threshold value of this C by equating these two terms. If these two terms are equal, then the whole will be 0. So, if it is sitting in the threshold of being oscillatory to non-oscillatory, and when you do that, I call this damping term as critical damping term, because that is the term or that is the value of the damping coefficient which is at the threshold of the system turning from oscillatory to non-oscillatory or vice versa. And therefore, Cc, because I can then call this as omega n, and then it Cc turns out to be 2m into omega n. Okay. That is the critical damping coefficient for you. Okay. And that critical damping coefficient is having its own units, right, just like the damping coefficient has its own unit. Okay. So, it makes more sense to introduce a term called as a damping ratio, as and mostly denoted by zeta as C over Cc. So, it is basically a normalized damping of the system, normalized why? Normalized with respect to Cc. You may notice that for a given system, this critical damping coefficient is a function of the system parameter like m, k, right. So, for a given system Cc is fixed, it is a constant value. So, for a given system, the damping, actual damping in the system C is normalized with respect to the critical damping coefficient Cc. So, this is sort of a normalized damping value zeta. It is all called as the damping factor or a damping ratio, and it is a ratio of C over Cc. Okay. So, now if we go back to this particular expression, C over 2m is the term that is appearing in both cases, that I will write here C over 2m as I want to get rid of the C. So, C over Cc and Cc over 2m, and I will replace the C over Cc as the damping ratio or damping factor. Cc is already shown as equal to 2m omega n, and therefore, this is 2 zeta, sorry, this is equal to zeta into omega n. Okay. So, C over 2m takes the value zeta omega n. Okay. Now, what I do is I can now write this these two roots as minus C over 2m is minus zeta omega n and plus minus square root of C over 2m is zeta omega n. So, zeta omega n square minus omega n square, and therefore, this becomes minus zeta omega n plus minus omega n. If I take outside, this becomes zeta square minus 1. So, these are the expressions of the two roots. Okay. Now, in most mechanical systems, this normalized damping is typically less than 1, mostly. Okay. We shall take the case when they are, when zeta is not less than 1, but to start with, if zeta is less than 1, then it makes sense to use this expression or reformulate this expression, write it like this. Of course, this is with the assumption, definitely with the assumption that the damping ratio is less than 1, because if it is less than 1, I can write the two roots as minus zeta omega n plus minus j omega d, sorry, omega n. I should write this as one minus zeta square. So, the two roots for an damped vibration case is minus zeta omega n plus minus j omega d. Now, where omega d is the damped natural frequency and is given by omega n into square root of 1 minus zeta square. So, these are the two roots of the vibratory system. Please make a note, single degree of freedom system, one natural frequency, two roots, and these two roots are what? They are complex conjugates. Okay, minus a plus minus j b, these two are the two complex conjugate roots of this vibratory system. And then therefore, the general solution, as we have been writing the general solution x of t to be a e to the power s 1 t plus b e to the power s 2 t. Our initial assumed solution, if you remember, was so x naught, although we wrote it, this was the assumed solution, because we got two roots and both roots should be accounted for in the general solution. So, that is why this S 1 will contribute, S 2 will contribute, and the total response will be simply addition of the two terms. So, now as we notice that both S 1 and S 2 do have a common real part. So, therefore, this is how it has been done. If you really see this equation to be going like e to the power minus zeta omega n and plus j omega d into t and plus b e to the power minus zeta omega n minus j omega d into t. So, those two roots, if you see, if I mean I can take e to the power minus zeta omega n t out as a common term, and that leaves us the bracketed quantity as a e to the power j omega d t plus b e to the power minus j omega d t. And whatever are the values eventually which you will get expressions for these a and b, ultimately this entire bracketed quantity turns out to be harmonic quantity, right, depending upon the value of a and b. Now, you remember we wrote x of t similarly for an undamped vibratory system like e to the power j omega n t plus b e to the power minus j omega n t, and then what we did was we got an expression from here for the velocity, okay, and then we implement impress the initial conditions at t is equal to 0 for both displacement and velocity, which because of those two equations the two unknowns involved A and B could be obtained, right. So, A and B were obtained in terms of the initial conditions x naught and v naught, which was which were basically the initial displacement and initial velocities. And similar thing will happen for the damping case as well, that A and B unknown constants will be obtained by using the initial conditions x naught and v naught. Now, that is an exercise which is to be left to you. You can the way we did for the undamped case, you can also find out by taking the derivative of x of t, getting an expression for x dot, and then by substituting t is equal to 0, x at t is equal to 0 will be x naught, x dot at t is equal to 0 will be v naught, and then you can solve those two equations to arrive at the expressions for A and B. It is a simple mathematical exercise for you. Now, more important is to discuss how do we make out of the roots that we have got here. I mean, definitely, as this part is going to be a harmonic one and this part is going to be an exponentially decaying term, the overall response, how would it look like? Although I showed you the typical response that we are all aware of, that it is going to be a sinusoid with a frequency equal to omega d. So, the time period between these two peaks for one cycle is going to be, as we can expect, 2 pi over omega d. Omega d is the damped natural frequency. So, that is the time period with which the vibratory system will oscillate, and depending upon the strength of the relative damping or normalized damping or a damping factor value zeta, the rate at which this amplitude decays will be decided. Okay. So, larger the value of zeta, faster is the decay in the response. So, this enveloping curve is actually this exponential quantity, and this oscillating part is basically coming from the bracketed term here. Okay. Now, you can definitely realize here that based on the value of in fact, not the value, but the sign of this real part, the response would be either decaying or exponentially increasing, right. So, obviously, as we notice here that this particular term is minus zeta omega n t, which actually shows that the response even if it is oscillating is actually decaying in its amplitude, because this typically is going to govern the way amplitude is going to change. However, by any chance if this real quantity turns out to be positive, so if S1 and S2 are like some positive quantity plus minus j b, where b represents the imaginary part of the root, and if this a is by any way or any chance, if this turns out to be a positive value, you can definitely know that this particular term, which has the real part in its exponent, is going to create, no matter how these oscillations are dictated by this bracketed quantity, the amplitude of those oscillations are going to grow with time, because it is going to be e to the power a into t. So, it is this exponential part is going to create an exponentially exploding or exponentially growing response, and that is what we call as an unstable system, obviously, because as time progresses, after the system has been perturbed at t is equal to 0, we expect the system to gradually come down to its mean equilibrium position, but by any way, I mean if by some configuration of the system, depending upon what system that you are analyzing, it may happen, although this is relatively a rare phenomena, or chance that you will always get your systems to exhibit negative real part, but in some cases which one or two cases we might discuss in future, that you may have an exponent with the real quantity in the root as positive one, and then that creates an exponentially increasing amplitude, which essentially mean that the system is not a stable one, but an unstable one. So, what are we learning from this? That this part is actually a part which is indicative of the stability of the system, because no matter what these omega d value is, or whether this is positive or negative, the system is going to show oscillations. So, the real part is indicative of stability behavior of the system, whereas the imaginary quantity is going to be your frequency of oscillation. So, that basically is the takeaway from this discussion, that when you get the two roots of a damped vibratory system, the real part gives us an idea on stability of the vibratory system, and the imaginary part gives us the damped natural frequency of the system. And therefore, before we even jump into the forced vibration response calculation, it is therefore usual for the designer to carry out eigenvalue analysis on the system, because through eigenvalue analysis you get all the roots of the vibratory system, and once you get the roots, you also immediately come to know whether the system is stable or unstable by just having a look at the real part of the complex eigenvalue. And if you have all the roots with a real negative real part, then the system is stable. Okay. So, it is therefore an important activity in the vibration analysis to carry out eigenvalue analysis. It is not only for getting the natural frequency estimation, as you see, because the complex eigenvalues or complex roots will give you an idea of the natural frequency of the vibratory system, but the real part gives us an idea about the stability of the system. Natural frequency of vibration is important from avoidance of resonance, but as you are now noticing that the complete understanding or idea of the roots of the vibratory system will also give you an added information of the stability of the system. So, this is what I mentioned, that if this real part, if it is positive, so zeta omega n, if it is greater than 0, this is all the response is going to grow with time. Although there are oscillations, and here also the time period here is going to be corresponding to the damped natural frequency, but these oscillations will grow in their amplitude after every cycle. That is the main important takeaway of the two complex conjugate roots that we just derived. Okay. Now, obviously, as I mentioned, it is your in a small mathematical exercise to extract the value or get an expression for A and B based on the initial conditions. I shall give you the final expressions that you can get for A and B, as well as when you substitute A and B and rearrange these exponential quantities within the bracket. Once you solve it and finally get the expression, you can get the expression something like this. So, what you see here is A has turned out to be this quantity and B has turned out to be this quantity, and that is the final response which you get completely identified. You can see that the response is now for a given vibratory system having its own k, m and c values. is dependent on these initial conditions x naught and v naught, right. So, at t is equal to 0, how much initial velocity or how much initial displacement or how much both of them, if they exist together, will decide what is the overall vibratory response with as a function of time. That vibratory response will have its own oscillation frequency, which is going to be dependent on the mass and stiffness and damping. As you notice that this is going to be a period which is going to be dependent on omega d, and we have already seen that omega d, the damped natural frequency, is omega n square root of 1 minus zeta square. The rate with which these oscillations will decay will be governed by the amount of damping you have in the system. Larger the damping, faster is the decay, and so on, right. So, this is the expression that you expect by solving for A and B. You can reorganize the terms within the bracket and can write the same expression in a slightly different form. If you remember, we have done that earlier for the damped vibration, undamped vibration case. So, on these two quantities can be clubbed, and then instead of that what you have is capital X e to the power minus zeta omega n t cos omega d t minus phi I, and we know that this phi I is the initial phase lag, the expression for which are given here. So, once you get this expression, getting this expression is straightforward. The expression for capital X is given by this. Again, you can see that it is dependent on the initial conditions, and typical response would look like this. Okay. So, that is basically is your undamped vibratory system response. So, given your vibratory system, which you will convert from a physical vibratory system by making a simplified model something like this, which has its own k, c and mass values. If this system is perturbed at t is equal to 0, the ensuing vibration response can be obtained by the expressions which are given here. Now, in case if the damping is much larger, and in few cases you do get situations where the damping is designed to be much on a higher side, then the system would decay, I mean the response of the system would decay very gradually and without any oscillations, because now the value of zeta is greater than 1. So, over damped systems are characterized by the normalized damping to be more than 1. So, the actual damping C is more than the critical damping of the system CC, and again by following the same process you will find that there will be two terms in the solution, one with this root and the other one with this root, except that instead of square root of 1 minus zeta square, obviously you will have to write zeta square minus 1, which is what originally we got. And now you may notice again here that irrespective of zeta being 1, 1.5 or 2, the square root term here, the total value of this will turn out to be smaller than zeta, and then the total exponent eventually will be still negative. Okay. So, depending upon the value of A and B, which obviously is again a function of the initial conditions, you will have one term which is exponentially decaying like this, the second term is exponentially decaying like this, and the overall response might look for a given A and B going like this. Okay. Sometimes you might find that the response could be like this, but eventually it will all fall to 0, okay, as time progresses. So, in fact, overdamped system are very sluggish system, and in the sense that the system when they are perturbed initially at t is equal to 0 from their initial mean equilibrium position, the response comes back to its mean equilibrium position at I mean after a long period of time, right. So, that is one of the major issue, that we cannot have a system coming to rest after a long period of time after being disturbed from its equilibrium position. Okay. For example, as I always give this example of guns which have these recoil mechanism. Okay. So, the recoil mechanism of gun are damped systems actually, and then we do not want that the barrel to keep on oscillating for a long period of time, right. So, on one extreme the oscillations can happen for a long period of time if your zeta is too small, and if zeta is too large, oscillations may be avoided, but then the response coming to 0 will take too longer time. So, there has to be appropriate balance depending upon the practical requirement. If you want the system to come back quickly without oscillating, the damping should ideally be targeted to be zeta equal to 1, because with zeta equal to 1 there are no oscillations, and if this requirement is that there should be no oscillation, then the earliest you can arrive at the mean equilibrium position without oscillation is with the damping factor equal to 1. Okay. For example, the door closer mechanism that you have, you would not like the door to be swinging back and forth from its equilibrium position once somebody pushes it outwards. Those oscillations are irritating, and I mean no designer would like to have a very low damping for a door closer, but at the same time you would also appreciate that if the door closes after too long a period of time, it loses its meaning, because one has to wait for a long time for the door to get closed. So, a target would be without oscillations if you want, or if you are willing to have few oscillations like this, then you can have zeta close to 1, but less than 1, and so on. There are other issues like practical issues of if it is like a fluid viscous damper being used, then over a period of time the viscosity changes, there are dirt and dust, and then overall damping value will change. It will also change with time, with temperature. So, those issues needs to be addressed for choosing an appropriate value of the damping factor. We might take a couple of examples based on this. Again, here as you see, the overdamped systems will have their expressions for A and B, the two unknown constants from substitution of initial conditions obtained like this, and then you have a threshold damping case where the damping is critically damped, which means that zeta, as I mentioned, is equal to 1 for a critical damped system, zeta greater than 1 for an overdamped system. Then in that case A and B expressions turn out to be this, and the response looks somewhat like that. Okay. So, as you see, the response does come to a mean equilibrium position much faster as compared to a case where the damping factor zeta is way more than 1 or much larger than 1. Okay. So, just to give you comparison of how different systems oscillate and show their responses once disturbed from its equilibrium position, for an undamped case zeta equal to 0, you get a harmonic response without any change in the amplitude. So, that is how once disturbed it continuously vibrate without any loss of amplitude. It of course, is an ideal case, because we know that in a practical vibratory system there would be some damping all the time, and therefore, this eventually will lose energy and the amplitudes will fall. But theoretically an undamped system is expected to have the constant amplitude, as you can see here. The exponential term is clearly missing here, whereas the underdamped system will have this exponential term as a part of the response expression, which ensures that the value, the amplitude value keeps reducing. As you see, they will keep reducing in the amplitude as the time progresses. And of course, critically damped system or even over damped system will have this is the over damped system, and critically damped system will have no oscillations in their response, and the expressions are given as you see. So, from the mechanical, aerospace and even civil engineering domain, we will always find the response or the systems to be underdamped systems, and therefore, the rest of our discussions will be focused on underdamped system, sometimes with undamped system also, but critically and overdamped system are relatively not common, and therefore, we will stick to the discussion on underdamped or undamped systems. Okay. So, the other important parameter which is having its practical relevance is a parameter called or a term called logarithmic decrement. Okay. Just like damping factor is a ratio of C over Cc, the actual damping in the system over critical damping of the system. Logarithmic decrement is used more often than the damping factor in practice in practical vibration measurements, right? And I will discuss why is that so, but it also is a measure of how quickly the initial vibrations decay. In fact, zeta or the damping factor also in a way is a measure of how fast the vibrations or how quickly the initial vibrations die out in an underdamped case. But there is a distinct relevance and importance of the logarithmic decrement, that is what we shall discuss. Now, we all have seen the amplitude of free vibrations of a damped vibratory system given by capital X e to the power minus zeta omega n t cos omega d t minus phi I, is not that is the expression that we had, right. This is the response at any instant of time t. Now, what we shall do is we will set our time equal to 0 at this point, okay, or let us call this time as time t1 and this time after one cycle of oscillation as time t2. Okay. So, in a damped vibratory system, if the oscillations are decaying gradually, I can say that this is my response at the start of let us say this cycle, and the response after one cycle is let us say x2. So, I am saying that this is the response at starting time t, and you all agree that I can set this time at any location along time axis. So, if I call this t as t1 and maybe this t2 x2 at time t2. Okay. You also know that the time between these two peaks is our time period of oscillation. Okay. All right. So, this is a general expression for the response. I can use this to get the value of the response at time t equal to t1. So, x 1 is actually x at t is equal to t1, and how much will that be? It will be simply by substituting minus zeta omega n, and this t I will substitute with t1, and then this is going to be cos omega d t1 minus phi I. Is that okay? Now, the response at time t2 is going to be x2. So, x at t is equal to t2 is going to be capital X e to the power minus zeta omega n t2 cos omega d t2 minus phi I. Now, obviously, you would agree that these two cosine functions after exactly one cycle are going to be identical in its value, right. So, cos of for phi I to be constant, obviously it will be omega d t1 and omega d t2, they differ in its value by 2 pi, isn't it. So, cos of the angle after 2 pi radians are going to be same. Okay. With that, let us look at what will I get as a ratio of x 1 by x 2. If you just check this and these two equations, it is going to be capital X e to the power minus zeta omega n t1, and these cos terms I will now ignore. I mean, they will be identical in the value. So, I can cancel it out. In fact, x also cancels out minus zeta omega n t2. So, what do? I can write this x 1 over x 2 as e to the power minus zeta omega n, what is that, t1 minus t2. So, I can use this as t2 minus t, isn't it. So, what is t2 minus t1? It is this capital T. So, the same expression I can write as e to the power zeta omega n, and capital T, we know that this capital T is 2 pi over omega n square root of 1 minus zeta square. It is 2 pi by omega d. Omega d is the damped natural frequency, we know that it is having an expression of omega n square root of 1 minus zeta square. So, when I substitute T2 by minus T1 by this expression, omega n will obviously cancel out, and what I will be left with, okay, is 2 pi over square root of 1 minus zeta square. Now, that is x 1 over x 2, right. So, if I take a natural log of this ratio, okay, then what do I get? So, I shall now write this as x 1 over x 2 equal to 2 pi zeta over square root of 1 minus zeta square, which is called as the logarithmic decrement delta. Now, the question is, if I already have a parameter like damping ratio which quantifies how quickly the initial response or initial amplitude decays or reduces, why should I have another parameter delta which does the same, right? So, the answer lies in the expression that we have here. If you want to know for your system how much is the damping factor, what will you do? You will need to know what? You will need to know your C, you will need to know your K, you will need to know your mass of the system. Now, think of a practical vibratory system, a complex a compressor sitting on some isolator, some structural members there, all of them contributing to some value of mass, some value of K and some value of C. Evaluating those parameters for complex vibratory system or even a simpler vibratory system is not that straightforward. It is not easy all the time. At least the damping will be always difficult to it. But look at this delta. The delta is definitely is related to the damping factors actually. So, which means that there is a direct linkage of delta with the damping factor zeta. Okay. Which means if I have this delta, somehow I already have a fair idea about the damping in the system. Now, it is also equal and related to what? To the ratio of the amplitudes of the vibratory response and free vibratory response, right. So, if by some means if I can perturb the practical vibratory system from its mean equilibrium position, I just perturb it at t is equal to 0 either by giving it initial displacement or giving initial velocity, and if it vibrates on its own free vibration response, and if I can capture that response using some sensor, which means that I am now talking about vibration measurements without knowing what mass the system has, what damping the system has, what stiffness the system has, right. So, if I can capture this vibratory response, measure it, and when I measure it, the sensor will give me a measured vibration response like this, and then from this measured data I can find what this x1 is, I can find this x2 is. So, from the measured values I can get to know the damping and the quality of damping, the level of damping in the system without worrying about how much mass the system has, how much stiffness the system has. Okay. So, knowledge of the system parameters or vibration parameter values is not essential here. Okay. All I need to know how to disturb the system from its equilibrium position and what sensor should I use for recording this vibration response. Once the vibration response is recorded, I can use this expression that we have derived here in assessing the damping in the system. That is the advantage we have. Okay. So, logarithmic decrement therefore is practically a very important parameter, because you can do a quick simple test on the vibratory system in situ and extract the damping information of the system. And if the system has low level of damping, let us say if the damping is less than 0.5, you will find that obviously, which typically is the case, most of the times our mechanical vibratory systems I have been saying that the damping is less than, in fact less than 0.1, it does not go beyond 0.1, all structural members do not have very high level of damping. So, therefore, one of the common practical expression being widely used is ignoring the denominator here, because it is going to be very close to 1, and therefore, by using this simple means, if I measure the response and get this delta value from this relationship, okay, I get the value of damping factor of the system. So, this expression is valid for zeta less than 0.4 or so. Okay. After that, of course, this denominator term starts becoming numerically larger, and the value that you get for zeta may not be very accurate, right. But for all practical purposes, delta equal to 2 pi z is basically the straightforward expression. Delta you get from the measured vibration data, and zeta can be obtained from it. Both of them signify that if the delta obtained is positive, you have a stable system. If you have negative, it is an unstable system. Okay. Obviously, because the zeta, if it is negative, minus zeta omega n t will turn out to be positive zeta omega n t, and the system will exhibit unstable response. Okay, based on this part, these are the recall questions. Kindly attempt these questions and then check how your answers are matching. So, the summary of this lecture basically had a detailed discussion of how the response of a simple single degree of freedom model is obtained, particularly when the damping is there. We obtained expressions for the response, how the system stability can be gauged from the real part of the complex eigenvalue. We also saw an alternate parameter of quantifying the decay of free vibration response, and that parameter was logarithmic decrement, and we observed how practically more convenient this logarithmic decrement is, which does not need the knowledge of the parameters of the vibratory system, and based on the measured data you can quantify the amount of damping in the given system.